All right, welcome everybody to another Danish Sound Cluster webinar. My name is Pedro, the usual host, and today I would like to introduce three very interesting guests and talk a little bit about the topic first. It's called Emerging Acoustic Sensor Technologies and Applications. So what does that mean? Well, it basically means that back in the old days, acoustic sensors were, there was not that many different types and they were quite simple. You had a loudspeaker and a few others. But now as technology evolves, we get more and more variations of sensors and also combinations of sensors that really maximize the audio products and audio experiences. And that's what we're going to talk about today. Different types of sensors and different takes on new stuff. I would like to say, at least introduce a little bit the speakers, but then I'll leave it for them, but at least say who they are and who they work for. And so Sergey Rodke Griffel, I hope I'm not saying that too wrong. Welcome. He's a principal scientist at Ericsson Research Center, which is a part of Dement. He's based here in Denmark. And then we have Dion Deroux, who is head of pre-development at Sonion in the Netherlands, I believe. And then we have Remy Gustavino, which is a director of product management at Grass Sound and Vibration, also here in Denmark. So welcome, guys. It's a pleasure to host you. Before we go, so I just want to explain how this works. Like always, we will have the three talks, and actually we were supposed to have four, but unfortunately Marie could not attend. But it's still plenty of material. I'm sure we'll have interesting discussions as well. And maybe Marie will be able to attend another webinar, which we are already cooking. So we will go through the three talks, and then we will take the Q&A at the end. So the Q&A is actually, there's a button on the bottom where it says Q&A. If you have any questions, you write them there throughout the webinar, and then we will take it all at the end. If you could specify the person you are asking your question to, that would help when we are reading the question. So just put the name there. If you have anything else to ask or talk about other than a question, then just put it in the chat and I'll take care of it, or my colleague Shelly will also be here in the chat. So this will be recorded. This will be online, so you can watch it anytime at your convenience, but hopefully you like to stay here and watch it live and participate. Otherwise, you can watch it a second time. We have plenty of events coming. Next week, we have we have one more webinar. We also have an in-person event. Go check our events. There's already a lot of signups, going to be very interesting. Different topics than this, but I'm sure a lot of people would like it. And just to end this introduction, there will be a survey, a small survey at the end of the webinar. If when you get out of the webinar, just spend 1 minute to give us some feedback. That would be great. So without further ado, I would like to invite Sergey to start. He starts with research. So it's a natural transition to the second talk and the third talk. So Sergey, welcome. You can unmute yourself and I will highlight you and off you go.
All right. Can you hear me fine and see my slides? Yes. And all is good?
Oh, perfect.
All right. So thank you for the kind introduction. My name is Sergey Rodke, and I am principal scientist at Ericsson Research Center, and as you pointed out, part of Oticon. And the presentation that I will be giving today is around a new sensor technology that we're actually quite excited about. Yes, that we're quite. Can I not get rid of this? Yes. Yeah. That we're quite excited about, that is ear EEG. So basically putting electrodes in the ear canal. and how can we use actually this sensor technology for audiological applications. And rather than focusing on one specific audiological application, I decided to show a bit the breadth of our activities. So basically go around different audiological applications that we see that could be of interest for our hearing aids in the future, for example. And since I'm covering a lot of ground, I'm also presenting work from our colleagues and collaborating partners. So that's mainly work from the Center for Ear EEG in Aarhus University and TNW Engineering. But for those that are a bit new to EEG itself, I just wanted to show how this actually looks like. So EEG, this is the typical EEG setup that you have. So you would have at the subject like this one in here. Let me just get the pointer up. And basically they have usually some kind of hat, a cap with a lot of electrodes on them. And then you see what Lawrence and Lina are doing here. They basically put some kind of gel, and that's just basically to get better contact between the skin and the electrodes so that you actually have a lower impedance and you get actually a better measurement. And what you basically do with this kind of setup is you will put a subject doing a specific task, and then you will monitor the brain waves and study these responses on like the effect of noise on specific hearing aid signal processing or whatever. But the technology that I'm going to talk to you about today doesn't look like this. As a starting point, it doesn't have gel. So what actually the ear EEG that I'm going to talk today about uses dry electrode technology. This basically means that you do not need to put any kind of lubricant. And we thought that this is a must for an application. I don't see like people wearing hearing aids and putting gel in the ear moles and then to try to get a better contact. So that would not fly. And the other thing is that we basically place the electrodes in the ear canal, and that's how it looks like. So basically, this is the, yeah, I cannot get rid of this. All right, that's fine. This is how it looks like. This is the evolution of our dry ear EEG prototypes. So basically, that was the first prototype that we developed at Ericsholm. Back when was that? 16, 17, I don't remember, within an EU project. And basically, maybe the next picture actually shows it slightly better. What you see is that we have an earpiece that is like a custom-made mold. And basically, we place some electrodes on this earpiece. And basically, I think in our typical setup, we'll have around 6 electrodes in each ear. And then basically, in this case, actually, the preamplification happens at the ear level, but it can also happen elsewhere. And technology is actually evolving quite a lot. I mean, we moved from something like this to something like this to actually something like this today. This is actually a research prototype that the Center for Ear EEG, that is led by Preben Kidmose at Aarhus University, is actually sending to space. So actually, this is part of the Sleep in Orbit project, where basically a Danish astronaut that is going to the International Space Station in June, I believe, will bring this actually up to space, and basically what they're researching is basically sleep monitoring. So the astronaut will be recording some sleep patterns on Earth, then some nights of sleep in the International Space Station, and then when he comes back. And honestly, this looks pretty neat and quite close to something that could be a commercial product. So I think we're all looking forward to see what is the future of this technology. And then, of course, back to Earth, back to Oticon, back to Ericsholm. What we're really interested on is on audiological applications of ear EEG. And we see this as a quite unique opportunity. Our hearing devices are located in and around the ear, so we have a quite privileged location already. And what we see the future of this type of technology is that we can actually look at maybe read people's mind, like basically read what people's brain signals and know what they really want to pay attention to, and know what they really would like to hear now. So without further ado, I'm going to go through the 3 different audiological applications. The first one is actually on using ear EEG to try to estimate gaze. Basically, here the idea is to try to estimate gaze so we could potentially steer a sound source. So you could imagine like steering a beamformer with your eyes, kind of. And this work is actually published in several papers. That the work that I'm presenting here today is in this paper in Frontiers in Neuroscience, and it's some joint work with Martin Skoglund, Martin Andersen, Martha Schill, Vera Kaiser, Michael Rank, and myself. And the main concept behind this is that we're trying to take advantage is that basically our eyes are like big dipoles, right? So they are positively charged on the front, negatively charged on the back. And if we put actually 2 electrodes, sorry? Yeah. If you actually put two electrodes on the temples, basically you can see pretty well where you're actually looking at. And what is more exciting is that you can do the same with ear EEG. So we set ourselves to this experimental setup in here, and where we actually wanted to see like, okay, how good does this ear EEG actually work to estimate, for example, where are you looking at in a 2-talker scenario. So we had 25 hearing impaired participants sitting in a chair like this, and roughly 1.8 meters in front, they had a large screen with life-size person. So this is like an 88-inch screen. And then the participants, like, that was supposed to follow this kind of conversation between these 2 talkers, roughly 20 degrees apart from each other. And they were basically doing this task, following a conversation, answering some question at the end, while we were monitoring their ear EEG signals by putting electrodes in the ear canal. And then as well, we had a golden standard system, basically a Tobii eye tracker to know where they were looking at each time. So basically what we were really interested is like, can we, from ear EEG itself, know if they were looking, for example, at the male speaker or the female speaker? And as a reference, we use the eye tracker. So the long story short, so what I'm showing here is just the results directly. So basically what we have in the x-axis is all the participants. What we have in the y-axis is attended speaker accuracy, and attended speaker accuracy is defined as like how much of the time the ear EEG estimator was telling their correct target. And as correct target, we refer to the target selected by using the eye tracking data. And what we could see is that in average, we had something like around 68% of target accuracy. So 68% of the time we were selecting the right target. But what was a bit more interesting to see is like, I mean, I did run a few of the experiments myself. And what you could see is that there were really some people that had excellent ear EEG signals. And with those people, actually, it was a quite nice progress. And you could see like, well, our estimate is actually working quite well, while some other people's really it was a bit hopeless. So basically, some people were just barely above a chance level, and that we do see with this technology. Some people have weaker signals than others, and we truly don't know yet why. All right, but I think that here, what we concluded is that, for example, using ear EEG, we can estimate who an end user is looking at least in this 2-talker situation, with roughly 68% target accuracy. So this was the first application domain that I wanted to cover. The second one is a bit more science fiction, and that is basically on trying to estimate cognitive load, right? So basically, you know, like hearing impaired participants, they do need to put this additional effort to be part of conversations, to live like a close to normal life. And they do get quite tired throughout the day. And especially when they reach towards the end of the day, they really struggle to focus. So here the idea would be, wouldn't it be great to try to estimate cognitive load, how loaded the individual is here and now, so that potentially, for example, we could adapt the sound signal processing. So now this individual needs more help. because he's quite loaded. Let's increase the noise reduction aggressiveness, for example. And the work that I'm here presenting is published in this article in here, and it's work done by Tirdat, Emina, Alvaro, Will Widmer, Lauren Hadley, Michael Ingrang, Thomas Luna, and Karina Graversen. And basically what we did in this experiment was, so we had normal hearing participants. This one was with normal hearing participants seated in a chair, and then they had the following task. They had to attend a frontal target speaker. From this speaker, we had like some continuous speech. I think it was some kind of fairy tale, like that lasts something like 33 seconds. And then at the end, they had a question. That was a comprehension-based question, trying to see if people actually were listening and comprehending what happened. And they had to do this while there were 4 microphones around presenting some noise. And the noise was set at a level that basically would have different SNRs, from a very challenging situation of -16 dBs to something quite positive, like 8 dB. And while they were performing this task, we were monitoring from one side ear EEG signals, but we also had, in this case, actually full scalp EEG as a reference. So basically what you saw, the cap at the beginning. And basically for you to get a feeling on what was the performance levels of the individuals carrying this task, you see here, like in white, gray, all the individual responses, and in black, the average. And you see that basically in average, when you were at a very positive SNR of +8 dB, people could actually perform the task at almost at ceiling at 90%, while they were at -16 dB. So they were quite challenged, and they were basically performing above chance level. And then, so what were we interested in here? Basically, among all the potential brainwaves, if I dare to say this way, that we could look, we decided to look at a specific frequency band, and that's the alpha power frequency band. So that goes usually from 8 to 14 hertz. And basically what I'm showing here is the full scalp data, so like from all the electrodes in the head. And then this is like the power, and here you have like the scale, and here you have time. So basically what you see is that over the course of all trials, all individuals, so we do have quite a strong activation on the alpha region. And the alpha region basically is here in the back, in the posterior region of the head. And what was more interesting was that, I mean, this shape is the alpha power activation at different SNR levels. And this plot does look very much like the performance plot, right? So you do have a higher activation at the positive SNR and a lower at the negative one. But what was even more exciting was that with the ear EEG data, you do get a similar trend as always with ear EEG. The data is more noisy, you need to denoise it better. I mean, look at the scale, it is a different scale, but we still did see some activation in the alpha region, in the alpha power. So that was actually very exciting. So this is like a bit of the conclusion of this study, and please use with cautious. But basically, what we find out in this study is that alpha power in this kind of continuous speech paradigm may actually indicate how well the speech was perceived. And it can be measured both using scalp EEG as well as ear EEG. So that's actually quite exciting to see that this actually works. All right. Then back to the last of the audiological applications that we are interested on. And that's just basically estimating hearing presence. And here the idea would be to have self-fitting hearing aids. And the work that I'm here presenting is some joint work with the Aarhus University. So that's Christian B. Christensen, Renske, James, Thomas Luna, and Preben Kidmorsen. And before I go a bit into the details of this work, I need to introduce a concept. And that's just basically auditory steady state responses, so ASSR for short. And ASSR is basically an auditory evoked potential. that can be used to basically objectively estimate a hearing threshold. And you usually use this type of methods to get a hearing threshold on individuals that cannot or don't want to provide a response. And for example, such an individual could be a baby. And it works in the following way. So you have a receiver unit in the ear, and that presents like a specific sound and a specific frequency, specific intensity. And then you do have some EEG electrodes that then measure a specific response. And you do a swap on intensity, and then you see like the response on the EEG. So it's a bit like a pure tone audiometry, but rather than having the individual saying like, yes, I can hear, you have the brain saying, yes, I can hear, if that makes sense. And then basically what we're interested is like, I mean, there are commercial tools available to do this. Can we actually use EEG for this? So here I'm just going to examine directly to the results. So bear with me. Let's go here in the left plot first. Here we have like the different frequency bands, 500 hertz, 1000 hertz, 2000, 4000 hertz. And what we see at the bottom ones are basically behavioral responses of the individuals that carry out this test. In red, we see a behavioral response to a pure tone audiometry. So basically the traditional thing that you do to do an audiogram. Can you hear this sound? No. Can you hear it? Then you keep increasing intensity until they can. And we also did like a chirp audiometry. And chirp is a specific sound that it sounds a bit like, and basically it was the same as a behavioral response. So basically they were presented with chirps, and can you hear this chirp, and so on. And what we see up here is the ASSR responses in pink for the scalp EEG, so basically traditional setup, and in blue and in green with two different ear EEG setups. And what is quite exciting to see is that first we can actually get the thresholds. So this is exciting. And we also see that this threshold seems to be elevated with respect to the traditional ASSR. And the ASSR themselves, they are also elevated with respect to the behavioral ones. But I think that this basically was done in hearing impaired subjects. And I think we consider this like as a proof of concept that ear EEG, this technology is actually a feasible method to estimate hearing threshold levels in hearing impaired subjects. Of course, the devil is on the details. So there is, from here to a commercial thing, there is a lot of work to be done. But I mean, this at least shows a potential path of how could this be actually used. All right. So now I've covered like 3 audiological application domains. And the next step is what I want to talk to you a bit about is what are we actually working on now? Going forward, what are we interested, what are we excited about on using this technology? So the first project that I want to talk about is a PhD project from NAN that is in the Center for Ear EEG in Aarhus. Before I go to his project, I need to explain the concept of auditory attention decoding. What is that? So for those that don't know what auditory attention decoding is, I mean, back in 2012, there was this first paper, I believe, that basically what they demonstrated was like, imagine that you have this task, you have 2 speakers in front of you, one that you're trying to pay attention to, one that you're actually trying to ignore. The speech envelope of the individual of the speech that you're actually trying to pay attention to gets better encoded in your brain than the one that you're trying to ignore. The one that you're trying to ignore, it still gets encoded, but in a significantly lower resolution, if that makes sense. So basically, if we measure EEG, we can know if you're paying attention to the right speaker or the left speaker, because you can basically reconstruct the speech envelope. And then say like, oh, the speech envelope of the right speaker is better, is more accurate than the left one. And then basically you know where you're trying to pay attention to. And what NAN is actually trying to do is like, okay, we know that we can do this from full scalp. Can we do this from ear EEG? And can we also use, he's actually using another approach for this problem. So we're actually quite excited to see where his PhD work may be leading to. And then another project that we're actually very looking forward to see the results is Heidi's project. Heidi is a PhD student with the Center for EEG as well, but she's actually sitting with us at Eriksholm. And basically her project is around neural correlates of speech intelligibility. So long story short, I mean, we do a lot of speech intelligibility tests at Eriksholm and in the hearing aid society in general, right? And basically we have like a hearing noise test, and then we test like, different algorithms, and then we see this one yield better speech intelligibility or not. But what Heidi is trying to answer is like, can we actually obtain an objective measure of speech intelligibility from EEG data? So basically, can we avoid people actually providing a response? That would mean that maybe we could, if we can actually do this from the ear EEG, that means that we would have like a speech intelligibility estimate 24/7 in our hearing aids. Wouldn't that be great? So that's what she's trying to answer, and of course is still in the research phase, but that's something that we're very, very excited about. And then another PhD project that I wanted to mention is Rebecca's PhD. She's a PhD with the DTU Health Tech department, and her PhD is in and around mental state fluctuations of engaged listening. And basically what she's trying to answer is like, okay, can we know if somebody's actively listening by looking at EEG, both scalp and ear level? And if so, if they are actually listening, can we know something more about their mental state? Are they fatigued? Are they stressed? Are they in normal state? Whatever that means. So that's what she's actually trying to answer. And the last but not least project that I wanted to mention is Anna's PhD. She's a PhD student at Aarhus University, the Center for EEG again. And what she's actually doing is a bit of this ASSR work, but with a quite peculiar case that I found very exciting. So basically, all the ASSR work has been mainly done using like chirps, some very unnatural sounds that you can easily fall asleep with. But Anna, basically what she's trying to do is like, can we actually use natural sounds? And in particular, can we use speech for that? So basically, she just uses natural speech. She modulates a bit that speech in a way that is barely perceivable, but that basically provides some kind of ASSR response, and that you can actually measure it with the EEG. So that's what she's actually doing. And there is a lot of math and a lot of denoising tools and a lot of things behind it. But it is actually, that would mean that we could potentially have a hearing aid 24/7 providing an updated audiogram. We get a cold, then we know that we get a temporary hearing loss. The hearing aid will be able to cope with that. So just to put an example. All right, I think that was as much as I wanted to cover for today. I just want to acknowledge some of the people that have contributed to this work. A lot of Eriksholm colleagues, some former colleagues from Eriksholm, and big thanks to Preben Kidmose from the Center for EEG in Aarhus, and TNW Engineering and the University of Nottingham. And for those that would like to see the science behind, here you have some papers. I think that you will get a recording of these, and otherwise you can always write me an email. All right. Thank you very much.
Super exciting. Thanks, Sergi. I will spell your name correctly now.
Good.
I did hear you saying it. Wow, super exciting. I have some questions, but we need to keep going. So Dion is up next. Dion is kind of a natural flow from Sergi because but it's more in the commercial applications, but I won't spoil it. So whenever you want, Dion, you can share and fly.
Let me share my screen. Let's see if this.
Just need to full screen, and then we're good. Yes, that's good.
Yes. Yeah. No, it looks good. Also on my side.
Perfect.
Okay. Yes, my name is Dion de Roo, and I'm head of development of the receivers and rigs at Sonion. What I'd like to present you today is first a short introduction to Sonion for the ones who don't know us. And then the main topic for today will be the biometric product that we developed, which should enable real-time health monitoring in the air. About Sonion. Sonion was founded in 1974 and is owned by Novo Holdings today. And we are a business-to-business supplier of components and solutions for the hearing instrument and high-end audio device industry. And we innovate, we design, develop, and manufacture products for the industry. And our main customers are the 5 big hearing aid manufacturers in the world, where we currently have around 50% market share. We are with 6,000 employees that work in the various facilities around the globe. We have our R&D center in the Netherlands, where I am located, and we have a production plant in Vietnam, and we have sales offices in Denmark, US, and China. So our focus areas for Sonion, well, the core is that we serve our standard hearing aid functionality with our components like the receivers. The receivers are the loudspeakers, it's hearing aid nomenclature, the microphones and receiver in canal assemblies. Next, we also see hearing aids and consumer hearables converging, for which we support products that enable features that are expected from smart earbuds or features that enhance sound quality. Here we also have some interesting products that we could maybe present in another webinar. And finally, the health area, where we see that the hearables and health monitoring actually goes really well together. And that is actually the topic that I would like to elaborate a bit more on today. So the Sonion biometric, that is a commercial product, and as mentioned, the hearing aids have become and will become even more multifunctional in the future. An example of adding functionality to hearing aids is the possibility of measuring heart rate and other biomarkers to a hearing aid. And at Sonion, we developed a product for this, which is the Sonion biometric. So what is it? The Sonion biometric is a speaker unit assembly that produces sound for people with mild to moderate hearing losses, combined with an integrated heart rate or PPG sensor. And this product can be used for both fitness or sport activities, as well as health monitoring purposes. And we have developed this product together with our technology partner, Vadencell, that is located in the US. I would like to tell you a bit more on this product and also its features in this presentation. So what is the background technology that we use in this product? First, a few words on that. Well, the background technology is PPG. PPG is a measurement technology that uses a light source and a photodetector at the surface or an enclosed surrounding of the skin. And PPG is used to detect volumetric changes in the blood flow. And it makes use of low intensity infrared light. And when light travels through biological tissue, it is absorbed by bones, by skin pigments, and blood vessels. And since light is more strongly absorbed by blood than by surrounding tissues, the changes in blood volume can be detected by the photodetector by the changes in light intensity of the reflected light. So now with each heartbeat, the blood is pumped through the body and blood vessels will swell and contract, and changing the blood volume in the vessels. And this heartbeat travels as a pressure pulse through the body, which can as such be detected by the PPG sensor, and then delivers the PPG signal waveform as is depicted here in the bottom right of the slide. There are actually quite many products on the market that work with PPG sensors. You may recognize a few of the ones that are shown here. And they measure on different locations on the body. And each measurement position on the body comes with pros and cons. Some solutions are highly visible, others are less comfortable to wear, and not all solutions are therefore suited for continuous measurements. And since our target group is hearing aid users, which are elderly people and usually health conscious, we specifically interested in a highly invisible, comfortable, and suited for all day wear to do continuous measurements. And of course, all that with a high accuracy to measure heart rate and other biometric markers. And measuring in the ear canal could deliver on all those benefits. And a big plus is actually that there's a high blood perfusion in the ear, and that the skin tissue is very thin in the ear. And that actually results in quite high PPG signal levels, making the inner ear quite a good place to measure, and which is also confirmed by a number of scientific articles. This has actually initiated the development of the biometric, and that's why I would like to show you how the product actually ended up looking like. And later I will elaborate a bit more on some of the tricks and solutions that we have implemented to overcome some of the difficulties in measuring in the ear. So what is the product? Well, again, we developed this speaker unit assembly where we included electronics to drive the 3 LEDs to illuminate the skin, an optical sensor to detect the reflected light from the skin, a motion sensor to compensate for head and body movements, and of course, last but not least, the acoustic speaker to compensate for mild to moderate hearing losses. It's not a given that such a system fits within existing hearing aid architecture. Hearing aids are low power devices and usually fully optimized for sound processing, and yet less for other data processing capability. So reducing the power consumption while maintaining high measurement accuracy was, for instance, one of the trade-offs that we had to optimize. And in practice, actually, that meant that we did several design iterations and prototype iterations on the position of the LEDs, and also on the drive currents for those LEDs. We tested each design iteration on multiple people and also with different activities. And doing that way, we found the optimum locations of the LEDs and the settings for those LEDs. So how can the biometric be integrated into a hearing aid? So that's depicted here. We have again our loudspeaker assembly, the biometric, on the left, including all the electronics and sensors. The measured PPG data is then transmitted over an I2C line to the main body of a hearing instrument, triggered when requested by the hearing instrument. The hearing instrument is in control, and the hearing aid is equipped with a DSP and a Bluetooth chip. And on either of those chips, a few lines of driver interface codes must be programmed to communicate with the biometric speaker unit. And also that driver interface code is provided by Sonion. Then we have the cell phone that collects the sensor data through a wireless connection with the hearing aid. And the app on the cell phone is equipped with the Valencell's PerformTech library code. And this library code is specifically designed and programmed for the biometric. The app on the phone then runs the algorithms to convert the raw measurements into biometric values like heart rate and heart rate variability and possibly other metrics as well. And the PerformTech library code is available for both iOS and Android platforms and is also provided by Sonion. So this is how the product looks like and how it's integrated into a hearing aid. But there are some specific challenges to measure in the ear canal. For instance, if we so variations in position and complex body movements can all introduce measurement artifacts, and some are actually specifically related to in the ear canal measurements. So if you go from left to right here, for instance, during talking, jaw movements can introduce movements of the ear canal, like circular motions and even compression of the ear canal. Next, also the blood circulation and the perfusion areas within the ear canal can also differ from person to person. Then again, the insertion of a hearing aid, each time or every morning the hearing aid gets inserted in the ear, the speaker unit might sit slightly different in a slightly different position in the ear. And of course, not to forget the head and body movements can also have effects on the position of the speaker unit in the ear, or can introduce other movement artifacts. So there are quite some variations to take care of. Well, to overcome most of those mentioned measurement artifacts, we have, together with our development partner Vedencel, developed a smart system. The biometric is equipped with 3 LEDs, and that is for a special reason. And we developed an algorithm that continuously, on a regular basis, decides about the best LED combination to eliminate the skin of the inner ear. And with the 3 LEDs, we have 7 combinations possible. And for each of the combination, the signal-to-noise ratio or signal quality indicator is then calculated. And the best combination is selected until a new best combination is found. And the best combination, that can differ per person, per insertion, or also per activity the person is doing. So while most of the PPG sensors products work with only 1 LED, the biometric works with 3 LEDs, and this redundancy in the number of LEDs gives us a way more robust and stable and accurate PPG signal. So again, if we go to these disturbances that we have identified when measuring in the ear canal, we can counteract these disturbances by different solutions. The combination of using the multiple LEDs, the selection algorithm to find the best LED combination, and the use of the motion sensor can mitigate many of the measurement artifacts due to motion and position. Going here from right to left here, the micro movements from head and body that can be detected and compensated for by the motion sensor. While for the other situations, our multiple LED algorithm comes into play and is very effective there. And all these solutions are combined in the Sonion biometric system. In order to test the accuracy of heart rate measurements with the biometric, we have made use of CTA test protocols that were executed in our in-house biolab. The CTA test protocols are meant to evaluate continuous heart rate measurements for consumer electronic wearables during sedentary exercise or everyday living activities, but not necessarily for hearing aid use cases. So we selected 6 of these CTA tests, and we added a new one here called the Sonion SRT4 test. And this SRT4 test was added to test accuracy during talking, which we find an important activity when wearing a hearing aid. And we know that it is a difficult listening situation or measuring situation for in the ear canal measurements. The SRT4 test is detailed out here and contains a number of periods where the test person is asked to have a conversation or to read the text, sometimes even in combination with doing a physical activity at the same time. So all in all, this SRT4 test is quite a severe test protocol to pass. In general, the CTA test protocol requires a test population of 20 people minimum, with a variety in age, sex, skin tone, and BMI. And heart rate is then continuously measured with the device on the test. biometric and with a reference calibrated chest strap. And then the pass criteria for the CTA test is set to have less than 10% deviation between the biometric and the chest strap measurement over the complete test population and test protocol. Maybe a quick sidestep on how we did the measurements and how we tested that in our biolab. Let me see if this works, and I would like to show you a short video on our test protocol and how we tested the biometric in-house. So you see that we have the test participants coming in. We used Sonion employees, but also external guests from outside. Of course, we took care of the privacy and personal data of the people. And as you see that the people are wearing a dummy hearing aid behind the ear. That's not a commercial hearing aid. That is just let's say a test vehicle for us to power up the biometric. You also see that people are wearing a headband. That is actually in that headband we integrated a wireless communication to transfer the data during the test protocols, and we did also benchmarking with some other commercial available PPG sensors, as you see. But this is actually how the tests were performed. I will stop the video. Oh, the video is actually already ended. So. Maybe let's zoom in on how the biometric performs on heart rate measurements during talking, and actually the effectiveness of our multi-LED solution. The SRT4 test, as said, contains different activities, including several periods where the test person talks. And if we isolate those periods and we plot those results separately, then actually we note that during the talking, the measurement error is highest. Here you see quite some deviations in the measurements from heart rate during talking, which is of course in line with the statement that during talking the ear canal makes many different movements and rotations and can really create disturbances in the measurement. However, if we then switch on our multi-LED algorithm, we see a huge improvement over all the activities, but actually we see a major improvement around the talking activity. So here we can say that especially for talking, our free LED solution really excels. So, so what is the overall accuracy of heart rate measurements with the biometric? Following the CTA guidelines, as I just explained, and the test protocols, the Sonium biometric meets well within all pass criteria, and it confirms that the biometric measures heart rate accurately and stable over a wide range of lifestyle activities. And also from benchmarking with other wearables, we know that the biometric can compete with the most accurate wearables, that is hearables and also wrist-worn sensors that are on the market right now. So next, as the Sonium biometric is shown to measure heart rate accurately, we've also tested the RR interval, or the beat-to-beat interval accuracy. And with accurate RR interval measurements, heart rate variability can be derived. R to R interval is actually the time between the heartbeats. And heart rate variability is actually the fundamental parameter for further health assessments. And to measure HRV, that requires tracking of really small changes in the range of milliseconds in the intervals between successive heartbeats. And this is different, of course, from heart rate, which just averages the number of beats per minute. Unfortunately, there's no real industry standard test or pass criteria to test the accuracy of RR intervals. The best practice is to plot the statistical parameters of RR interval measurements and check then the correlation with chest strap measurements under sedentary resting conditions. And also here we found that the biometric has high correlation with the chest strap measurements, and that gives us high confidence that it also can be used for more sophisticated metrics for now and in the future. And actually we have some proof for that already. Some examples of more sophisticated metrics we have tried out, and also have shown to be possible with the biometrics. Two are explained here. One is stress, the other one is atrial fibrillation detection. Going into stress detection on the left. For stress detection, we have set up a Stroop test, in which we have a test person that is asked to read one color while another color is displayed on display in front of him within a short limited amount of time, and hereby introducing confusion and stress to the test person. And it's found that this stress can actually be detected by analyzing both the heart rate and the heart rate variability data coming from the sonium biometric. So, and detecting stress can, for instance, be a very interesting measure for listening efforts or fatigue amongst hearing aid users. And I think in the previous presentation that was already mentioned that these kind of use cases are really interesting for hearing aid users. Another interesting metric is the detection of atrial fibrillation, AFib. In a cooperation with FibriCheck, we have actually proven that the data coming from the sonium biometric can be used as quality input for FibriCheck's medically approved AFib detection software. And by this, the hearing aid with a biometric and a phone app equipped with the FibriCheck app would make the hearing instrument suitable for detecting AFib amongst hearing aid users, which again, of course, may be a very interesting use case for hearing aid users. And that this is just the start of maybe more interesting use cases to come. And well, there may be many more. And of course, we at Sonium will be happy to investigate any of these use cases or maybe new use cases with any one of you. So thank you for your attention, and thank you for listening.
Thank you, Dion. Very, very good. Yeah, I've again, thinking, there's a lot to talk about this. I mean, you've been trying different metrics and measurements. There can be so many things done with this. You also made me think about the listening effort and all that, because I know there's a lot of investigation going on. Cool. All right.
Thank you.
Thanks. Let's go then to Remy. Can you share your screen, Remy?
Yeah.
So there was some relation first and second topic, some not entirely, but now it's a very different sensor application for acoustics, and it's more basically reinventing the microphone again. So go ahead, Remy. The stage is yours.
Thank you. So I'm going to talk about a new microphone we've been working on at CAS. A bit about myself, Remy Gustavino. I work with product management. I've got a PhD in acoustic in measurement methodology. I spent 12 years at Bolon Care in R&D, product management, and I was also working on smart sensor. And I joined CRAS in 2020. And I've been working mostly on this new microphone. So I've got a short agenda. What is the problematic with audio measurement? Where can we help? Then I will show this new technology. I will explain the user benefit, and then I will conclude with what did we learn. So why is it so hard to perform acoustic measurement? And I've tried to look at that user. I think a huge percent of the acoustic measurements that are performed are not performed well or in a nice way, and it could be some human fault, like, but it could be also because people don't really know how to use a microphone, and especially how to correct a microphone for sensitivity or frequency response, for example. So that's what to start. You could start. You've got two ways. Either you could work on the user and try to educate him more and explain him how to use a microphone. And that's what I've tried to do in the past, but it didn't work so well. And then you can also work on the measurement chain and make it easier for the user not to do something wrong. So I think the user, it's mostly at the university or during courses when you learn to measure. I've been focusing on the measurement chain. And that's a typical measurement change, acoustic measurement change. You've got a microphone, an audio analyzer, then PC and software, and some cables between, but cable doesn't mean really anything in this kind of situation. So if you change PC, if you change some software, you might see some really small difference when you're measuring. So your uncertainty might change a bit, mostly because of different kind of software algorithm or something. But it's so small. If you change sound card, then if you buy a good sound card, so the difference between two good sound cards are also minimal. So it won't mean almost anything for your uncertainty budget. But changing microphone, that means a lot. Two different microphones, even of the same type of microphone, they can have different sensitivity, different frequency response. So that can be a big part of your measurement uncertainty. So that's where I try to focus. So we identify what we want to work on. Where should we do that? We've got two different kind of school. We've got the measurement microphone, that's what Grass has been known for, which is really high quality microphone where quality is a key decision factor. Usually the user is highly trained in acoustics, so you know how to apply a correction, you know how to correct for sensitivity. And then you've got a production line microphone where cost is a key decision factor, but where the user is often untrained in acoustic, and when correction are not always applied. Sometimes you only correct for sensitivity, and sometimes you don't correct for anything. So this first microphone is a production line microphone, so it is used to measure some simple device like headphones or mobile phone or smart speaker. And like I told you, key is a key decision factor. So if you look at the production line microphone, this is a population of 100 precision production line microphone. So they are quite cheap. They are an order of magnitude cheaper than measurement microphone. But if you look at the spread in sensitivity, and on a measurement microphone or production line microphone, sensitivity is measured at 250 Hertz. So that's how many Pascal you get, the millivolt per Pascal. So then you've got a huge spread in sensitivity. And if you look at the frequency response, then you've got some microphone with a big peak on the high frequency, some microphone that go really down. So you've got a huge uncertainties that is due to this cheaper microphone, we'll say. So we agree that we could make a difference on this production line by having some microphones that don't have the same kind of uncertainties. When it says production line are really conservative, so that we need a better sensor, but we need also to keep the analog output because it should be backward compatible. So you should be able to use this new microphone on the old production line. You need to keep the exact same form factor because it should be a replacement. They don't want to build some new production lines. They just want to change the microphone, so it's also cheaper. The good thing is we've got a lot of new technologies that are commercially available, some small DAC, digital interface, digitalizer, sound card, how do you want to call it? So what we did, we created a microphone which is use an analog sensor, a condenser microphone, but then we use a digitalization process to make this signal digital. We can correct for gain and sensitivity and for frequency response, and then we can make it analog again. So this microphone isn't changed on the outside. It's the exact same form factor, the same stick, the same kind of conditioning, but everything is corrected with this new Acoustic technology. That's how we call that. So basically, we managed to fit a small microprocessor into the preamplifier with a kind of complex equalization and a gain, which means that out of the box, you get a microphone with a fixed sensitivity. Like I showed you before, sensitivity can vary up to plus minus 2 dB normally. On this one, the sensitivity vary plus minus 0.2 dB. And a flat frequency response. So it's much easier to mount it on a production line. So it's also cheaper. Then it reduces the measurement complexity because you've got no equalization or no sensitivity settings to apply. So you speed up the installation time and you can use the existing interface. This is what you do normally when you got 100 microphone out of the box. Either you use it as it is, and then you can live with the uncertainties. Or what you can do is first adjust the sensitivity, and this should be individually done. And if you got 100 microphone, it could take a long time. But this is easy. So the difficult part is to equalize all this microphone. So they've got a flat response, and you've got to individually equalize them, and you've got to know which microphone belongs to which correction or which correction belongs to which microphone. It's a really difficult, and I've done it a lot, so I know what I'm talking about. This is a difficult practice. So what we managed to do, we managed to do a microphone which is already from the factory, adjust from sensitivity and from equalization. So no gain, no equalization needed. It's flat. And this is what you get without applying anything. Just putting your microphone into your sound card. That's also good because on a production line, for example, if a microphone breaks or if something happens, then you need to stop the production line. You need to call a train user, so maybe an acoustician that has to exchange a microphone and then to find a way to compensate for sensitivity and for frequency response. And that could take time. With this kind of microphone, if something happens, you just take it away, put a new one. It will be the same than before. And why is it important? Because if your microphone is, for example, underestimating the high frequency, it means that you can, on a production line, you can have a good unit, which is classified as bad because the imperfection of your microphone will put your device outside production limits. So a good unit measured with a non-uncorrected microphone can result in a failed test, and you will have to put it in a trash. But the worst is if you've got a good unit but maybe as for too much high frequency, then using a wrong microphone, it can be classified as good, and then you will be sending your customer a defective product, even if you have tested it and even if you think it's a good one. So having 4 microphones that got the exact same frequency response and gain will mean that all this part of the production chain will measure accurately and will measure in the same way. Now, if you got a microphone with different frequency response, you can see that that this guy will use this green microphone, which will overestimate a lot the high frequency, and this one will use this black microphone, which means that he will be underestimating. So what we've done with this one, we solve many customer pains by having all this intelligence into this microphone, and it is not like super intelligent, it's just really practical, and it will help any user not making mistake during equalization or sensitivity check. So if you use this microphone, you less likely to get different results using different microphone or multiple microphone. This new microphone is also an order of magnitude more stable with respect to environmental condition because of the new sensing element we've been working on. You won't have any long setup and replacement time because all the microphones are 25 millivolt per Pascal. So all the microphones got the same sensitivity, the same frequency response. You don't have to individually correct anything. And replacement, you just take it away with a new one, no correction needed. This also means that because you're not correcting and because all the microphones are alike, then your measurement uncertainty will be much smaller. So you have some much better measurement. So what did we learn? Because we learned a lot. In the beginning, I was thinking of a super USB microphone or Wi-Fi microphone, but measurement world, especially on production line, is really conservative. So if they've got something that is working, they don't want to change it. If you can show them that you can make something, you can make them gain money, maybe they will try, but it shouldn't be a big change. It should be small incremental changes. It also shows us that in 2023, almost all the big manufacturing company we talked to use analog acoustic sensors that didn't go to the digital world yet. So all these ideas of having a super fancy USB or a Wi-Fi microphone was not something we could talk about. So I think we made a difference by using this new digital technology and by adding it into the microphone preamplifier. So, and if you ask me, this is the first real step in acoustic sensor technology for a long time, and I've still got a lot of ideas to make it better and to make it easier for the user, because all this work is done to ease the use of microphone, because I've seen too many people mismeasuring, because it's complicated, it's not easy, and you should be able to focus 100% on your measurement, on your doing. You shouldn't think about measurement technique and compensation, and you should be able to focus totally on your measurement. That was a bit shorter than the other, but that's what I've got.
Yeah, it's great, Remy.
Thank
Thanks
you.
a lot. Perfect. Really, really exciting.
Hmm.
All right. What then
Oh,
maybe you can stop sharing and
yeah.
then we can start the Q&A. I can see that Siko is also here. I don't know if he wants to join, but he's also welcome to. So just to give a little intro, Siko is also part of Sonia, and he put the on here. But yeah, it's up to you, Siko. No pressure. So you guys can unmute. The Q&A is open. It's kind of empty, but that means everybody understood everything. That's not a bad thing. So normally it comes as we go. But I would say first of all, do you guys have any questions for each other? I think that's a good place to start.
I do.
Perfect.
And mainly to Dion. And I think I mean I have like maybe like 5-10 questions, but I'm just gonna cut it short. Like one key aspect of hearing aids is like comfort. So basically, you can wear them 24/7. You don't notice it. We've worked with ear EEG. You put like something in the ear canal. People can wear this, like it's a prototype. They can wear this for like like a few hours, not a full day. So what about your biometric solution? Is it comfortable? Does it fit in all ears? Do people complain? It's just more of a
That's a good question. Well, actually, we made on comfort. Actually, we did not really change the mechanical design that much compared to normal hearing aids. I mean, we still, if you look at the biometric, it still makes use of a dome, and the dome is kind of industry standard for all the RIG instruments. So actually, we do a contactless measurement. That's how we have implemented it. The LEDs do not make direct contact with the inner ear, so it's a contactless measurement, and in that way, it's it's as comfortable as any other RIG instrument.
I may assume that it's a bit more heavy, for example,
Yes,
because
I
there
just
are more
wanted to-
things in there, and then like on the dome, like maybe that puts a bit more. That's what I meant.
I just wanted to add that it's of course it's a little bit bigger than a standard speaker unit, and of course also a little bit heavier in that way. We are not aware that we got complaints from the market, but maybe that's maybe indeed up to the hearing aid manufacturers that to come back on that. But as far as we know, no, it's just as comfortable as a.
It also looked a little bit longer, right? It was a little bit longer.
Yes. Yeah. Correct.
Can I keep on going, Sachi?
And I was actually happy to see your 3-LED solution, because I mean, it's like the ear canal is a messy place to measure anything, and we do the same with the ear EEG. We put a lot of electrodes, not so much because we need a lot of them, but it's because if this
How many?
We put 6, but you can put like 12, but or more. But like there is not a lot of additional information that you gain. You basically put so many for redundancy. If this one is down, the other one will be up. And I'm happy to see that you're also applying this kind of rationale.
Yeah. What about the fact that you have 2, right? Does that also help you?
Definitely. So a lot of the all the applications that we have are basically cross-referencing. So like from electrodes from one side to the other side, and that does provide a lot of help. If you do like single-sided things, things get more complicated.
And you, Dion, as well.
Yes, we also, well, not in this application, but indeed we learned the hard way indeed that the ears is quite a messy place to measure as well. I mean, it makes a lot of movements, and every ear is different. It really differs from person to person. So in the end, we just found out that we need have redundancy in the measurement system to cope with that. Of course, we settled down on 3 LEDs, but yes, if we had the chance to put even more in it, maybe we would even go for even more LEDs. But for now, 3 LEDs was a good compromise and gave us good accuracies. Yeah.
Or maybe a disco ball with a lot of mirrors. I don't know.
Yeah. Also had to deal with power consumption in the end. So
right,
yeah.
passive then.
That was always a compromise and a trade-off to make.
Cool. Any more questions, guys, you might have for each other?
I mean, I can go on, but there are
Go
some Q&A questions I see now.
Okay, let's take a look
we
then.
can take them. But, yeah.
So Clement asked, regarding the Sonion solution, how sensitive are the sensors to the earwax temperature, humidity, and sometimes the smaller size of the ear canal?
But
Yeah.
those are a lot of questions in one. Of course, yeah, the ear canal size. Yeah, I mean that's the. It is a bit longer, so probably if fit rate, it will slightly go down. It will not fit in all the ears, but we also have done fit rate tests where we could fit most of the test persons. So we are still able to get good fit rates, mechanical fit rates. How accurate it is for wax testing, for wax and for humidity, I think that was also the question.
Yeah, earwax temperature, humidity, and size.
Of course, we do our environmental testing on all our products. We've also tested the biometric after extensive environmental testing, before and after. The LEDs are not so, I mean, they're completely encapsulated by epoxy and they're completely shielded from the environment. So for temperature and humidity, there's hardly any effect that we see there. They're very robust against that. Earwax, well, the sensors are actually behind the dome. So most of the earwax is actually powered up in front of the dome and do not enter or not, travel complete towards the LEDs and the optical sensor. So in that way, it has this natural protection from the dome already. If indeed wax ends up at the LEDs or at the optical sensor, yes, of course, then some accuracy will be degraded. But I mean that there are quite some layers of protection before it ends. Really, wax ends up there. Yeah.
I was also thinking about what about something like the stigma that you already have in hearing aids and the fact that there's light coming out of the ear canals, even though it's a bit silly, but have you considered that?
Yes.
Is that a problem? Or
it could be a problem, but this is infrared light.
Okay.
So it's
All
actually
right.
not visible. But if we would use visible lights, yes,
That would be
maybe
silly,
that
right?
could be an
Yeah.
could be an issue. Yeah, we have not
Exactly.
investigated that further, but it crossed our minds. Yes, but
That's
for now,
good.
for this product, it's not an issue. Yeah.
Perfect.
Yeah.
All right. So the next question is interesting solution on the grass microphone from Tony Torres Rosel. How does the analog to digital conversion and the digital to analog conversion affect the inherent noise and THD performance of the resulting microphone?
That's a good question from a microphone expert, I can see. It's clear that it's a kind of trade-off of compromise. You cannot get everything. So for this solution, we've been trading accuracy and flat response and fixed sensitivity against a dynamic range. A classical CCP measurement microphone has a dynamic range of 125, 130 dB. This is not really needed on a production line. That's very important in a laboratory or when you want to be able to measure really low level or really high level with the same microphone. but it's difficult to measure this really low and really high level at the same time. And usually on a production line, you've got quite a high noise floor, so you want to play high enough so that you get above the noise floor. That's what you're looking at. So it affects the THG, so it affects the high part of the dynamic range because it's difficult to find a analog to digital converters that got this 130 dB, and then that is really so small that it can fit in a microphone that is less than 4 millimeter long. So it's a trade-off we've done, which is it's a good trade-off on a production line. It might be not such a good trade-off in a laboratory that depending on what you want to cherish more, like accuracy or
Cool.
dynamic range.
Okay, so in other words, if you limit the range, maybe it's not too limited, but still you don't go to the extremes, then you'll have the same performance as what people are used to.
Exactly. So on this one, it's the first one we've got a bit more than 90 dB dynamic range, which means that if you're testing a headphone, for example, you can play all the way up to 120 dB SPL. There's not so many handfuls that need to play so high sound pressure. Or if you're measuring on a mobile phone, there's no mobile phone that are able to give 120. So it's a trade-off for sure, but it's not something that we find out to be a no-go on a production line.
No. Could it be a solution that sometimes you have like a setting that you can choose a different range? Could that be a solution in the future?
That could be a solution in the future. That might be something we're looking at.
Cool. That's great. Okay. Do you guys want to ask more questions to each other?
I have a question to Remy, actually.
Yeah.
I was wondering, the calibration of this microphone, can it also be done over time, or is it just a one-time calibration when it comes out of production?
So depending what you're calling for, what is calibration? If you're
If the
talking
microphone
about
sensitivity ages over time, or
that, okay. So
degrades over time for some reason.
yeah. So this is normally it shouldn't move. We have some samples that we are measuring like for almost 2 years now, and they didn't move. But it's like a normal. It's got the exact same dimension as a measurement microphone, so you can always put a calibrator on top of it and check the sensitivity. That's not problematic. That's like any normal measurement microphone.
Okay. Yeah.
I can ask a question. Would you consider integrating things into the KEMAR, or doesn't make sense? Or I don't know if it's confidential, but maybe you can say.
No,
Whatever
it's not confidential. Like I told you, we're looking at integrating this new technology in more products, and having it in a Kemaku could be a big help for calibration for. Yeah, so it's less sensitive because usually people that are using a camera have this huge expensive audio analyzer, and they can read TEDs and read sensitivity, and they can read this calibration file and compensate for. So it's less problematic than on a production line where people are untrained and don't really know much about measurement technology, at least the people that are on the production line. That's why we decided to start with less educated user. But for sure, it is having some smartness and something that makes your life easier as a user is something that I'm really advocating for. So it might come in a camera soon.
Yeah, I would guess the KEMAR might also be used for some production lines, right? So maybe in that sense, I don't know. I'm just supposing.
Yeah, we've got some simpler cameras that they use on production line. Yeah.
Yeah. Great. Cool. Sergi, you look like you want to ask something.
Yes,
Go ahead.
I was holding it. No, then again to Dion. So I could see in the small video that you showed that you had a lot of like reference systems, and I was not sure which reference system were you showing. So to be very specific on the question, I could say that you had like an Empatica Android device that is if it wasn't, it very looked like one. It would look very similar. So what's the accuracy like to such a golden standard system as that one, for example, of your heart rate and heart rate variability measurements? I know that you showed some errors, but I don't know to what did those errors refer to.
Yeah, I don't have those numbers I had here. The numbers that I showed in the presentation are the MAPE numbers. Now I have to mean average percentage error. So that's the deviation between the device on the heart rate measurements on the device on the test compared to a chest strap, a reference.
Okay, that's your reference. Okay.
Yeah, and that's over 20 people over the complete test period.
Okay.
So
that was like 5%. That's very good.
Yes, yeah, below 5%. Yeah, indeed,
Yes.
depending on the activities. Yes.
And then I had a question because, as you said, like the ear canal is a very messy place to measure. When you eat, when you speak, like there's so and that's why you have, I guess, an accelerometer in there, as you said, like to do something about it. So my question is, and you may say like I cannot reply, and that's also fine. But how much? I mean, I assume that you do some kind of artifact rejection. So when there is too much noise, probably you cannot do any recording. Do you lose a lot of data when speaking?
That's actually the availability parameter. That's also in the test results. So we have the MAPE number. That's the mean average percentage error, and we have the availability of data, and that's all. In most of the tests, it's all above 85% up to above 90% of the data. And indeed, sometimes the algorithm rejects data because it's not accurate or not. We cannot trust the data, let's say, and then we throw it away. But then that's also being tracked. Yeah.
Excellent. And then my last question, and then I'm done. You can have actually 2 years, right? Potentially. Like I guess that your solution is basically tailored for 1 year. Can you rely in synchronicity between should you have 2 years with 2 biometric?
Yeah.
Like what would be is it can you get like quite good synchrony on data collection between both?
Yeah, that's another study I think that we still need to do. Of course, that also the algorithm to actually assess both of the data streams coming from both hearing aids at the same time, and then decide which one is if we go for the left measurement or the right measurement. Yes, it's something also that crossed our minds how to deal with that. But that's maybe one of the next versions that we need to.
No, but I was fishing more like for synchrony, like like are they in sync? So like could you rely on I assume not, but I mean that's anyway. That was just.
It sounds like you didn't put that much focus on it.
I
cannot really answer that one. No,
it sounds more like a BLE a challenge than a sensor challenge. Cool, guys. So Sergi, just because you didn't get any questions, I'll just ask you a question. So you talked a bit about doing audiograms, quote unquote, for babies, and we know that OAEs or autoacoustic emissions is the main technology for that for many years, but we know that it has many limitations. And it made me think about that. Like, could it be that in the near future or in sometime we can actually use this ASSR approach that you were describing in a more standardized way for doing this kind of measurements. And even to replace audiograms, I don't know, but it made me like, wow, okay, if that's true.
I think I will hear like to which extent ASSR could replace AOE. I honestly don't know. That would be more a question that I would ask our colleagues at Interacoustics. But I mean, I believe that they have equipment for both. But the other question, I think, with respect to can these ASSR measurements replace audiograms? And I think they actually can. But there is a very beautiful and simple and cheap way to do these audiograms. That I mean, it's a bit like the industry. If it works, don't jinx it. It's a bit hard to fight against, but of course, that would make a lot of sense.
Yeah, just think about how you can integrate this in just about any hearing device or headphone or whatever, and standardize it somehow. And also, OAEs don't really work in hearing loss, right? So it's kind of like you do a measurement. So and if you can use this for a threshold of hearing loss, that sounds very powerful to me.
I honestly believe that the Eclipse product from Interacoustic can do that. I believe so. I'm not 100% sure, but I would think so.
Awesome. Well, guys, do you have any last words? Because otherwise we're already over time. So you seem good. So I want to thank you all for participating. It's been a pleasure. I hope you had fun as well. This will be available online for everybody to rewatch. And there's a small survey after people close this. So please help us out with feedback. And have a lovely day. And see you next week, I guess.
Thank you.
Thanks, guys.
Bye.
All right. Bye-bye.